Before we get into the different types of spectral classes, we're going to learn who came up with that classification system. Make sure that you've read this FYI before we go any farther. There it is. If you guys could write down the questions of the day in your science journal, I'd appreciate it. What characteristics help us organize the stars, and who determined those characteristics? We're starting with the second one. Who determined those? We're going to learn about probably the most important person in the entire field of star classification. You guys can write some of this down. The more you have in your science journal, the more helpful it's going to be. A quote from a person that did this: "Classifying the stars has helped in all studies of the structure of the universe. No greater problem is presented to the human mind." If you want to know about space, you study stars. You can see stars. There's a lot of them. If you want to know about galaxies, you study stars. If you want to know about planets, you study stars. If you want to know where we come from, you study stars. Studying stars is what astronomy is based on. And so classifying them is a foundation, a beginning to all of astronomy. Who said this? Obviously a really smart scientist. Here's a list of their education and awards.
They graduated from Wellesley College back in 1884. They became a student of astronomy at Radcliffe College, 1894. Received a master's from Wellesley College in 1907. An honorary doctorate from the University of Delaware in 1918. The first woman to receive a doctorate of astronomy from Groningen University. The first woman to receive a doctorate from Oxford. Another doctorate from Wellesley College. A doctorate from Oglethorpe University. A doctorate from Mount Holyoke University.
As you can see, very well respected, intelligent, very well educated. Her name is Annie Jump Cannon. Born in 1863, right smack dab in the middle of the Civil War. Died in 1941, right smack dab in the middle of World War II. She was born in Delaware, 1863, and she suffered a handicap when she was very young, which made her very hard of hearing. When she was at Wellesley College, she pursued physics and astronomy, two things that are very closely related. After she graduated, she became an expert in this brand new field. You may have heard of it. It's called photography. She loved to travel, because who doesn't? And in 1892, she went over to Europe. And you might think, okay, that's a big deal. We can get to Europe in a matter of hours. But back before the turn of the century, back in the 1800s, traveling to Europe was a couple weeks long on a ship. It was a huge deal. So virtually everybody born in America had never been to Europe. She took her camera over there and took a number of really cool photos and came back, and at the World's Fair in Chicago in 1893, she put together this little pamphlet with all of her photos of her travels over in Europe. Because the average person hadn't been to Europe, her little pamphlet sold extraordinarily well. Even though she loved photography and she loved to travel, she wrote this in her journal. She said, "I am sometimes very dissatisfied with my life here. I do want to accomplish something so badly. There are so many things that I could do if only I had the money." Yeah. And when I think that I might be teaching and making money, that isn't real, and still all the time improving myself, it makes me feel unhappy, as if I were not doing all that I can. Basically, after she graduated, she wanted to continue learning and improving herself, which is why she went back to school so many times. This whole time she was taking care of her elderly mother, but after her mother died, she went back to Wellesley College as an assistant in the physics department, and then became a student of astronomy at Radcliffe. Now, you may not have heard of Radcliffe College before, but Radcliffe College is right down the street from this little school named Harvard. Harvard, when Annie Jump Cannon was around, was an only male school. Women were not allowed. So Radcliffe was like the girl version of Harvard. Obviously that's not the case anymore, and Radcliffe College is now part of Harvard University. But back in the 1890s, women were not allowed to go to school at Harvard. It was only men. And so down the road, it was the girl version of Harvard, Radcliffe College. So she basically studied astronomy at the girl version of Harvard. That's a very bad way to say it, but that's what it was. While she was there, she took part in the very first X-ray experiments in the entire country, and then she started working down the street at Harvard at the Harvard Observatory. This is her I'm really hoping that she is just posing for this photo, because as a student of astronomy, you should know that looking through a telescope during the daytime, you're not going to see much. So I'm pretty sure she was just posing for this photo. Sarah Whiting was her teacher while she was at Wellesley College. This is Sarah Whiting. This is Sarah Whiting's lab, one of the first women to have her own lab. She started the astronomy department at Wellesley College, which is an all-girls school. She got a doctorate. Sarah Whiting got a doctorate degree from Wellesley, and this is Annie Jump Cannon standing right behind her. This is where they were doing the experiments on X-rays, the very first ever experiments with X-rays. This is her getting a doctorate from Oxford. There's evidence that there was teaching going on here in 1096. This has been a college for almost 1,000 years, and Annie Jump Cannon was the first woman to receive an honorary doctorate from Oxford. And here she is doing her actual work. In 1896, she was hired by Pickering, who was the head of the observatory at Harvard, to catalog and classify variable stars. Variable stars are important because that is how you can tell how far away things are. That's how we know how far away the Andromeda Galaxy is. That's how it's part of the distance ladder. So it's very important to catalog these variable stars. While they were doing that, they also wanted to classify them based on their spectrum. These little lines that we learned are absorbed by different elements. Different stars are going to give off different spectrums, and so they wanted to be able to classify them based on that. So here is Pickering, who was in charge of the Harvard Observatory. Here is Annie Jump Cannon, and next to her is Henrietta Leavitt. Henrietta Leavitt is the one who figured out that variable stars can tell us distances up in space. Pickering was the head of the Harvard Observatory, and Annie Jump Cannon is the person who basically classified stars based on their spectrum. As you notice, there's a number of women who worked at the Harvard Observatory, and they were known as computers. It wasn't really a derogatory term. It was more the fact that these women were brilliant and could do math that most other people could not do. So they were basically there to compute, to do math. This team of women computers took astronomy to a whole new level. So what did Annie Jump Cannon do? This is an example of one of the glass plates that she would be looking at. And she could recognize within a matter of seconds the type of spectra that was coming off of a star based on these plates. In about 15 to 20 seconds, realize, oh, this is this type of star, and she would be able to classify it. Over the course of her entire career, she classified hundreds of thousands of stars. She was the undisputed queen of classifying stars. She also helped come up with the classification scheme that we still use. So what is that classification scheme? What are some things that we could use to classify stars? Maybe their temperature, their color, very closely related. What about their size? Their size is sometimes hard to tell, but their spectrum is always exact. We can tell exactly what their spectrum is. So let's take a look at a few ways that we've classified stars. Obviously, we've done it based on brightness, from a 1 being the brightest down to a 6 being the dimmest. After just plain brightness, we realized that spectrums existed, and there was a guy who worked at Harvard by the last name of Draper, and he basically came up with his classification scheme, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, based on the types of spectrum lines that were present when looking at stars. As you can see, depending on the star's temperature, the spectrum that the star gives off is going to look a little bit different. And classifying them can be a little bit complicated. There's a lot of overlap. For instance, star A has strong hydrogen lines, which means there's a lot of hydrogen in that star. A B-class star is like class A, but with the addition of Orion lines, which turns out to be helium. So class A and class B are very similar. Annie Jump Cannon came along and realized that it's easier to classify them just based on their temperature. And when you do that, you get rid of all those repeated properties that Draper had come up with. If you reorganize them from hottest down to coldest, it makes it a whole lot easier. And it also turns out that there's a temperature and mass relationship. So using the spectrum but organizing them based on temperature turns out to make a lot of sense. So Draper had A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. And then Annie Jump Cannon got rid of all the repeated properties and rearranged them based on their temperature. This slide took me about 40 minutes to make, so we're going to look at it again. We started out with Draper's classification, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Annie Jump Cannon got rid of all of the repeated properties, and then you rearrange them based on their temperature. And this is what we are left with, O, B, F, G, K, A, M, which means stars are classified by spectral class. Their color, their temperature, and their spectral lines all play into this. O, B, F, G, K, A, M. O is blue. You guys have already written this down in your science journal. So these letters are their spectral class, and within that, there is a temperature range from the hottest O star to the coldest O star, then the hottest B star to the coldest B star, where 0 is the hottest, 9 is the coldest. So O0 is going to be the hottest star that you can get. And then O1, O2, O3, O4, down to O9. O9 is the coldest O star. And then you would have a B0, which is right next to O9. Then you would go B1, B2, B3, B4 to B9, and then A0, all the way down to the coldest type of star, which would be M9. And then you throw in their magnitude. If you remember, magnitude is their brightness, and that is going to have a lot to do with how big the star is. We've already used numbers, so now we're going to use Roman numerals. We're going to talk about this a little bit in a day or two, but you have 0, 1, 2, 3, 4, 5, 6, up to 7 in Roman numerals, and that tells you how big the star is. So if I give you guys on a test the star classification, it's going to have B, K, M, F, A, G. It's going to have the spectral class. Then it's going to have the temperature within that spectral class. And then it's going to have the magnitude classification, which will tell you its size. Of these different stars, which one is the hottest? Of these stars, which is the coldest? The coldest is an M-class star, so that would be Betelgeuse. Our star, our sun, is a G2. So it's a little bit colder than a G1, but it's hotter than a G3. If you guys could answer the questions of the day. If you are interested in these women who completely changed astronomy, there's an article right here, but there's also a wonderful book called The Glass Universe. It's called that because the plates that they looked at with all of the stars spectrums on it were made out of glass. And it's a wonderful book. And there's a link to this book right there as well. I couldn't recommend this one more.